Welcome back to another few videos in Precalculus. Today we're going to be talking about three different things really quickly. The first is defining what polynomials actually are, what linear factors are, and multiplicity. So we've already been working with polynomials a while, but we haven't yet defined what is a polynomial. So polynomials are combinations, sums, and differences of positive non-zero powers of x. So we might have 5x to the third plus 7x to the 10th minus 8. We might have x to the fourth plus x to the third plus x to the second plus x plus 1. And these are just examples. You could literally imagine an infinite number of polynomials. And they're all sums and differences of powers of x that may have coefficients or might not have coefficients. And of course, we're including constant terms, but a constant term by itself, just 1, would not technically be a polynomial. X plus 1 is a polynomial, however. In fact, it is a linear polynomial. So linear functions, quadratic functions, cubic functions that we've been using for years in math classes, they're all polynomials, which is why we've been able to talk about polynomials without really defining what they are. Now, suppose we have a polynomial such as x squared minus 4x plus 4. We've reviewed how to factor this using our Xbox method for -4. So that would be -2 and -2. And so we can write this whole expression as x minus 2 times x minus 2. So notice that each of these factors are linear. The exponent on x for each of them is 1. So these are linear factors. And when we're able to write a polynomial as a product of linear factors, we call it a linear factorization. Or you can just say product of linear factors. We can come up with any type of product of linear factors. We could have something like x minus 1 times 2x plus 3, x minus 4, product of linear factors. If I instead had x squared plus 9 times x minus 1, this is not linear because I have that exponent of 2 right there. But we could actually factor that further. That'll be the topic of our next video. But for now, notice that if we look at these two examples, this function, expression, it's not really a function yet, but let's just call f of x to make it a function. This function has 3 different factors, and we could write the zeros of these factors. So our zeros, our solutions, are the numbers we plug into each factor that makes that factor 0, which is why they're called zeros. They might also be called roots, depending on your preference. So if we have x minus 1 equal to 0, and x is equal to 1. We have 2x plus 3 equal to 0, and 2x is equal to -3, and x is -3/2. And for this last one, take a moment, probably already have it in your head, and the solution is x equals +4. Each of these are zeros. Let's come back to our first one. We'll call it g of x. Well, x minus 2 equals 0 means x equals 2. And this one is the same, so it's x equals 2. So notice that for f of x, none of the zeros are the same. They're all unique. But if we look at g of x, this 2 appears twice because our factor appeared twice. So this is what the third thing we're going to talk about is, and that's multiplicity. So the multiplicity of a 0 is the number of times that that 0 appears in the linear factorization of a polynomial. This factor appeared twice, so the multiplicity is 2. Each of these factors appear only once, so the multiplicity is just 1. But there's something even more exciting, because this expression for g of x is not simplified. Instead of writing x minus 2 times x minus 2, we could just write x minus 2 squared. And now our 0 is x equals 2, and the multiplicity of this 0 is 2, which just so happens to be the exponent on that factor. So when we simplify our linear factorization, the exponent tells us the multiplicity of that 0. Now notice I've been saying the multiplicity of the 0. So multiplicity doesn't belong to a polynomial, it doesn't belong to a function, it belongs to each factor in the corresponding 0. So let's make up a function. We'll call this h of x. Let's say it's x minus 1 cubed times x plus 1 to the 5th power, and then x minus, I'll already use minus 2. So let's do minus 5. Now we can think of identifying the zeros and their multiplicities. So the 0, x minus 1, the 0 is just positive 1. And the multiplicity of 1 is the exponent, so that's 3. So we have the 0, x equals 1, with a multiplicity of 3. We have the 0, x equals negative 1, with a multiplicity of 5. That's from the exponent. And x equals positive 5, with a multiplicity of 1. Now you might be thinking, well, why isn't it a multiplicity of 0? Because it has no exponent. Well, if we don't write an exponent, it's implied that the exponent is 1. So the multiplicity can't be any smaller than 1. It can be as large as we want to make it, depending on the function. For example, if we have k of x equals x minus 7 to the power of 6,782, the 0 is x equals 7, and the multiplicity is 6,782, because that's how many times this factor appears if we were to expand it. The multiplicity can be as high or as low as we want, assuming that 1 is as low as it goes, and it's always a whole number. We can't have a multiplicity of 1/2. Another interesting thing about the multiplicity is that if we were to expand all of these, the degree of the function, the highest exponent, would be the sum of the multiplicities. So if we come back to h of x here, the degree is going to be 3 plus 5 plus 1. So that's the sum of the multiplicities. So that's 8, 9. So we would say h of x is a 9th degree polynomial. Our first term, if we were to expand it, would be x to the 9th power. So these three things, a definition of polynomials, what linear factors and linear factorization is, and what multiplicity is and how we find it, will become critically important as we try to graph polynomials, as we look at the fundamental theorem of algebra, and as we look at how can we completely factor a polynomial of any order.